Hello and good afternoon friends. Welcome to our series on natural products and spectroscopy. Dear friends, in our previous session we discussed on NMR spectroscopy in detail, and dear friends, we would like to tell you all that lots of the section was remained, so we decided to take forward the lecture and continue with our series on NMR spectroscopy. So dear friends, from where we left on NMR spectroscopy in our previous session, we are going to continue further from there only and would be discussing a lot more on NMR spectroscopy once again. Friends, for this discussion we have once again with us in our studios Dr. Vandana. Dr. Vandana is Assistant Professor in Department of Chemistry, Dayal Singh College, University of Delhi. If you have any set of questions in your mind regarding NMR spectroscopy, then you can ask questions live from Dr. Vandana by calling us in our studio. You can contact us through a toll-free number. Our number is 1-800-110-430. I repeat, our number is 1-800-110-430. So let's welcome our guest, Dr. Vandana, and let's try to understand more and more about NMR spectroscopy. Hello ma'am, welcome to the lecture.
Thank you so much ma'am. Hello viewers, in the series of natural product and spectroscopy, we have discussed about what is a spectroscopy actually is, and we have discussed about ultraviolet visible spectroscopy in details in previous lecture. We have discussed about IR spectroscopy, that is infrared spectroscopy, and we have discussed in previous lecture about the fundamentals of NMR spectroscopy, that is nuclear magnetic resonance. As you know, what is a spectroscopy? It is nothing but it is the interaction of electromagnetic radiation with the organic matter or molecule. For the compound which wants to elucidate the structure of organic molecule, we need to fall the radio electromagnetic radiations, and which electromagnetic radiation need to fall on the organic molecule, it depends on the particular thing which you needs to identify. That in case of ultraviolet visible spectroscopy, we understood about the conjugation, about the homonuclear, about the heteronuclear molecules. How can we detect these things on the basis of ultraviolet visible spectroscopy? We have discussed in detail about the IR spectroscopy also. For IR spectroscopy, we need to follow the infrared electromagnetic radiations on the organic molecule, and what part of the organic molecule we will elucidate in with this IR electromagnetic radiation. We have elucidate the functional group of an organic molecule, that which functional group is particularly present in an organic molecule. Then we have started NMR spectroscopy. For NMR spectroscopy, we have to follow the radio waves electromagnetic radiations on a organic molecule, and through NMR spectroscopy we come to know the number of protons in an organic molecule and the type of equivalent proton, or we can say equivalent carbon skeleton in organic molecules. We have understood what is the flipping, how the transition took place in NMR spectroscopy, and we have understood in the last lecture what is the fundamental study of the NMR spectroscopy. Let's continue the NMR spectroscopy. And for any kind of spectroscopy, we must keep in mind the relation of difference in energy, that is transition took place in a particular kind of spectroscopy, right? And this is equal to h nu, or we can say hc by lambda. This equation we must remember all the time, because whenever we need to elucidate the spectrum of an organic molecule, we must understand what is the interrelation between frequency, between lambda, that is wavelength of a particular electromagnetic radiation, as well as the energy. And you can see if the lambda increases, frequency decreases as well as energy decreases. So we can elucidate any spectrum in terms of wavelength, in terms of frequency, in terms of energy with this equation, that is E is delta E in fact will be equals to hc by lambda. And these are the various types of spectroscopy we are discussing in detail one by one. We have discussed ultraviolet, as I told you. We have discussed in detail IR spectroscopy. We are discussing now NMR spectroscopy, and we will discuss in detail definitely mass spectroscopy as well. That will tell us about the molecular mass of a organic molecule as well as the fragmentation pattern. We will discuss in detail while discussing the mass spectroscopy. And we have discussed nuclear magnetic resonance. It is a powerful technique and which helps us to characterize the identification of carbon as well as hydrogen framework within the molecule. We have told in earlier slides also. And the two more common NMR spectroscopy are HNMR and 13C NMR, because 12C NMR is inactive towards NMR, right? And we have discussed about the fundamentals of spectroscopy, NMR spectroscopy. Now, we have discussed a little bit about the shielding and de-shielding. Let's recap it. When a molecule is placed in a magnetic field, its electrons are caused to circulate as well as with the proton, and they are causing a secondary magnetic field. We have discussed this is induced magnetic field, and rotation of electrons about proton itself generates a field in such a way that at the proton it opposes the applied field, and same time or we can say it can also reinforce the applied field. Thus the field, when it opposes the applied field, the field felt by the proton will decreases, or we can say diminished, and the proton will said to be de-shielded. But if the induced field reinforces the applied field or increases the applied field, the proton feels a higher field strength, and such a proton is said to be de-shielded. Shielding shifts the absorption field upfield, and de-shielding shifts the absorption field downfield to get an effective field strength necessary for absorption. Now, NMR data processing. Free induction decay, that is FID, is Fourier transform. You can see over here to frequency domain, from time domain to frequency domain, to obtain the frequency. Which frequency? We know that a proton is processing around the against the magnetic field, applied magnetic field, that is precession. Precession is the condition when the frequency of a precession motion and the frequency of radio wave, that is the electromagnetic radiations which we are following on organic molecules, comes in a resonance. That is called a frequency of precession. For each different nuclei is different, and you can say this is Fourier transform to frequency, this time domain, and this kind of spectra you will observe in NMR spectrum. Nuclear magnetic resonance can identify these things. 4 different features of HNMR spectrum provide information about a compound structure. You can identify the number of signals, position of signals, identification of signals, as well as the spin splitting of signals. How can we detect the number of signals? The number of NMR signals equals to the number of different types of protons in a compound. Protons in different environment give different NMR signals. Equivalent proton gives the same NMR signal, and NMR does not distinguish between mirror images, or we can say enantiomers. Here you can see that if we see this molecule, this is CH3OCH3, it is a ether. You can see the environment along this proton, these 3 protons is similar or exactly similar with respect to this CH3. So the signal will be only 1 for both kinds of proton. Let's see this one. When we say this one, that is proton A types of protons, CH3, these 3 protons, it is in the surrounding with these 2 protons, while these 2 protons is in the surroundings with chloride and with these kind of protons. So these are 2 different types of protons, or we can say for these 2 different kind of protons, 2 NMR signals will obtain. Here also you can see there are 3 types of protons, 1, 2 and 3. We need to see the adjacent environment of the proton, and there will be 3 NMR signals. To determine how to determine the equivalent proton in a cycloalkanes, or we can say in alkenes, we have seen in saturated molecules. Now we are talking about the cyclic molecules and unsaturated molecules. First of all, we need to draw these protons not like this, but like this, that we need to see these kind of protons in this manner. And you can see that one type of for this, and same here you can draw this molecule like this molecule, like you can see all the bonds, sigma bonds present in this, we can say hydrogen proton or chloride ion. For this molecule you can see one type of proton, these protons and these protons are in similar environment, so only one NMR signal obtained. Here you can see 1, 2, 3, three types of protons, so 3 NMR signals will obtain. Here 2 types of protons are there, so 2 NMR signals will obtain. 3 types of protons, so 3 NMR signals will obtain. So we can say here that the number of equivalent proton will give you only one signal, and it depends on the environment, adjacent environment. Here you can see this is methanol CH3OH, 2 signal will be observed. Why? One because of this proton and another because of these 3 protons. We are simply looking over here the number of signals, right? And over here you can see this is an amine, ethyl amine, 3 NMR signals will obtain. These 2 protons are equivalent in nature, as well as these 2 protons are equivalent in nature because the same environment, left hand side as well as right hand side. These 3 protons are equivalent in nature, so one signal. So in this way there will be 3 NMR signal for this molecule. And for this kind of molecule, another, you can see these 2 protons are equivalent in nature, these 2 protons are equivalent in nature, these 3 protons are equivalent in nature. So how many signals we will get? 3, 1, 2 and 3. Same here, these you can see these groups CH3 and CH3. Look at carefully, the adjacent environment for this CH3 and for this CH3 is same. Here also left hand side CH and OH molecule, here also CH and OH molecule, so environment will be same and signal will be 1. For this proton, separate signal will be obtained, and this is also a separate, or we can say environment is different for this alcoholic proton, so a different signal will obtain. Another molecule you can see over here, these 2 protons are in the same environment as these 2 protons, so it will give you only one signal, and these protons will give you one signal, or we can say these are the similar protons or having a same environment at the adjacent position. Methyl acetate, 2 signals will obtain, paraxylene 2 signals will obtain. These methyl groups are in equivalent environment and these protons are in the same environment to each other. So this will give one NMR signal and these protons will give one NMR signals. Another case is here, look at this carefully, the case of 2-chloropropene. From this structure, one can expect here you can say only 2 types of NMR signal will obtain, but no, when we draw this stereochemical formula, you can see the adjacent environment for this H proton and this proton are different. Here you can see this is CH3 with addition to these protons, and there is chloride ion with respect to this proton. So these 2 protons are in different environment and will give 2 different NMR signal. Same here, these 3 proton will give a different signal. Another methyl cyclopropane, one can expect the 3 sets of protons, but actually 4 signals are observed, and you can see again the stereochemical formula. When we show these protons which are understood, you can see 4 NMR signals will obtain, 1, 2, 3 and 4. There are more examples, diethyl ether 2 NMR signals, 1, and for 2 CH3, propanol 3 NMR signals, 1, 2, 3 and 4. Here you will observe 3 NMR signals, 1, you can see for N-propyl format 1, 2, 3, 4 NMR signals will obtain. More examples are here, you can see tertiary butylamine. These methyl groups are equivalent with respect to these protons, so 2 NMR signals will obtain. again 1 NMR signals because these are equivalent in nature with respect to the adjacent environment. For this kind of, you can see these phenyl group 1, 2 and 3 NMR signals, 2 NMR signals, these methyl groups are equivalent in environment with respect to the adjacent hydrogen atoms. So, 2 NMR signals will obtain, one for phenyl group and one for methyl group. These were the number, we were discussing about the number of signals. Now the position. In the vicinity of the nucleus, the magnetic field generated by the circulating electron decreases the external magnetic field that proton feels. We have already discussed it, that is because of secondary magnetic induced field. Since the electron experiences a lower magnetic field as it should be in absence of electron, but that is not possible at all, it needs a lower frequency to achieve resonance. And lower frequency is to write in NMR toward a lower chemical shift. We have discussed in the last slides what is the chemical shift. To shielding shift the absorption field upfield. Here you can see this is the nucleus if it is not surrounded by the nucleus, but if it definitely it is surrounded by nucleus, so there is a effect, shielding effect, because of the magnetic field which is produced by these electrons. And this electric field will be decreases as in absence of the electrons, but when electrons are there, the field felt by the proton will be decreases because of the secondary induced magnetic field of electrons. The less shielded the nucleus becomes, the more applied field it feels. This shielded nucleus experiences a higher magnetic field strength. It needs a higher frequency to achieve a resonance. Higher frequency is to the left in the NMR spectrum and towards higher chemical shift, so shielding shifts and absorption downfield. We have discussed in the chemical shift, that is with respect to tau or with respect to delta. Protons near electronegative atoms, we should keep in mind, are de-shielded because a electronegative atom withdraws electron towards itself. So they absorb downfield. In a magnetic field, if we are discussing about benzene, 6 pi electron in benzene circulate around the ring, creating a ring current, and you can see what kind of ring current is there. The magnetic field induced by these moving electron reinforce the applied magnetic field in the vicinity of the protons. Thus the proton feels a stronger magnetic field as it feels in the absence of these circulating electrons, and have a higher frequency is needed for the resonance. Thus they are shielded and absorb downfield. You can see this is the circulating pi electron or inner ring current, and the protons are de-shielded. The absorption is downfield at 6.5 to 8 parts per million. Now, how the chemical shift get influenced, or we can say decreases or increases because of these factors, because of inductive effect we are discussing in detail, because of van der Waals de-shielding, because of anisotropic effect, because of hydrogen bonding. Let us discuss what is inductive effect. A proton is said to be de-shielded if it is attached with an electronegative atom, or it can be a group. Greater the electronegativity of atom, greater will be de-shielding. If the de-shielding is more for a proton, then its delta value will also be more. As the distance from the electronegative atom increases, the de-shielding effect will be decreases, or we can say diminishes. Greater the electron density circulating around the proton, greater will be the induced magnetic field. If it is in opposite direction, then greater will be the applied field required to overcome the shielding effect, or we can say for the resonance. On the other hand, electronegative atom or group withdraws electron density around the proton and thus causes de-shielding. Due to de-shielding, smaller value of applied field will be needed to bring about the protons to resonance. Greater the electronegativity of atom, greater will be the shielding effect on a proton, and greater the distance of electronegative atom, smaller will be the de-shielding because of the distance. In tetramethyl silane, that is taken as a standard for the reference for the chemical shift because of shielding and de-shielding. The 4 electron releasing group cause wonderful shielding effect, and hence tetramethyl proton, we can say all are equivalent resonance at highest field strength. Next effect is the van der Waals de-shielding. In overcrowded molecule, that is in bulky groups, it is possible that some proton may be occupying sterically hindered position. Clearly, electron cloud of a bulky group, or we can say hindered group, will tend to repel the electron cloud surrounding the proton. Thus, such a proton will be de-shielded and will resonate slightly at higher value of delta than expected in the absence of this van der Waals de-shielding, or we can say in less crowded molecule. Next effect is the anisotropic effect, or we can say space effect. The de-shielding effect on proton attached to carbon double bond carbon is higher than that accounted for the inductive effect only. Aldehydic and aromatic protons are much more de-shielded. Alkyne proton appear at relatively low value, and the values of delta, that is chemical shift, in each case can be justified by explaining the manner in which pi electrons circulate under the influence of applied field, that is it will cause de-shielding or shielding effect. Consider an alkene. If it is oriented that the plane of the double bond is the right angle to the parallel field, then induced circulation of pi electron generates induced magnetic field, which is diamagnetic around the carbon atom and paramagnetic in the region of alkene protons. The protons will feel greater field strength when it is parallel to the induced magnetic field. Hence, the resonance occurs at lower applied field. In alkynes, electronic circulation around triple bond takes place in such a way that proton experience diamagnetic shielding effect. When the axis of alkyne group lies parallel to the direction of applied field, the pi electrons are induced to circulate around the axis in such a way that induced field opposes the applied field, and thus proton feels smaller field strength, or we can say shielding, and hence resonance occurs at lower value, or we can lower value of delta, or we can say higher applied field. To overcome these induced magnetic field to reach at the position of resonance. In case of benzenes, loops of pi electrons are delocalized cylindrically over the aromatic ring. We have seen in the previous slide. These loops of electron are induced to circulate in presence of applied field, producing ring current, and the induced current is diamagnetic, opposing the applied field in the center of the ring, and is paramagnetic outside the ring. Thus, the aromatic protons around the periphery of the ring, which we have seen, experience a magnetic field greater in magnitude other than the applied field. Such protons are said to be de-shielded, and hence a smaller applied field will be required to bring them to resonance. It may be noted that protons held above and below the plane of the ring resonates at low value. So, we have to see the position of protons also, whether they are parallel or perpendicular to the induced magnetic field. When they are parallel, you can see that protons held above and below the plane of the ring resonate at lower value, where on the periphery they will resonate at the higher value of delta, or we can say lower value of applied magnetic field. Next effect is the hydrogen bonding. It has been found that a hydrogen atom exhibit property of hydrogen bonding in a compound absorbs at a low field in comparison to one which does not. The hydrogen bonded proton being attached to a highly electronegative atom have a smaller electron density around it, and being less shielded, the field felt by the proton will be more, and hence resonance will occur at downfield. The downfield shifts depends upon the strength of hydrogen bonding. Intermolecular and intramolecular hydrogen bonding can be easily distinguished, as the intramolecular hydrogen bonding do not show any shift in absorption due to change in concentration. enols show strong intramolecular hydrogen bonding, which is further stabilized by resonance. Due to this, a greater de-shielding effect is caused and absorption for such a proton occurs at a negative tau. It is due to the fact that acid exists as dimers, we know it. As a result of hydrogen bonding, a signal for carboxylic acid proton in ethoxyacetic acid appears in this range. In phenols, absorption occurs at between 8 to 4 delta, but if the concentration is decreased, that is, if the volume of the solvent, say carbon tetrachloride, is increased, then the absorption for this phenolic protons occurs upfield. In case of hydroxyl group, ion benzene is intramolecularly bonded with some other group. In the ortho position, the absorption for hydroxy proton may even occur at the negative tau values. And you can see this is the reference point in terms of delta. This value increases from 0, 1, 2, 3, 4 up to 10, and these values, or we can say these values in terms of tau. You can see the ranges also: 10 to 9 aldehydic protons, 9 to 6 aromatic and heteroaromatic protons. For olefinic protons, you can see the values 4.5 to 7.5 approximately. For alpha disubstituted aliphatic protons, the values you can see the ranges from 2.5 to 7 approximately. For alpha monosubstituted aliphatic protons, it is the range from 1.5 to 5.5. For acetylenic protons, this value comes in the range of 2 to 3 in terms of delta values. For beta substituted aliphatic protons, 1 to 2 values in terms of delta, and you can also calculate the values in terms of tau, because the delta value is equal to 10 minus tau. Now the choice of solvent. What solvent we should take while preparing the samples for NMR spectroscopy? It is more important. A substance free of proton should be used, as we need to detect the type of protons and the type of equivalent protons. So a solvent should be free of its own proton, which does not give any absorption of its own NMR spectrum. Solvent should be capable of dissolving at least 10% of the substance under investigation. These solvents differ considerably as regards their polarity. Clearly, NMR spectrum of a compound measured in one solvent may be slightly different from that measured in the another solvent because of different polarity. Hence, it is important to mention the solvent used when you are elucidating any NMR spectrum. As hydrogen bonding involves electron cloud transfer from hydrogen atom to a neighboring electronegative atom, the hydrogen atom experiences a net de-shielding effect. A higher concentration of hydroxyl, NH compounds, or we can say amine compounds, where there is a strong intermolecular hydrogen bonding, de-shielding of proton is greater and signal will appear at higher values of delta than that a low concentration compound. With increase in the temperature, the extent of hydrogen bonding falls. Thus, signal in NMR appears at smaller delta value at higher temperature. Dimethyl sulfoxide, that is DMSO solvent, it is highly polar solvent and can be used in the NMR spectroscopy. What kind of characteristic a solvent should have? It should be chemically inert, magnetically isotropic, should be devoid of hydrogen atom, should dissolve the sample to a reasonable extent. It has been found that the NMR spectrum of even completely deteriorated solvent does show one or more peaks. It is due to the presence of minor impurities in the solvent. And you can see the number of solvents which we can use for the detection of particular kind of protons, or we can say in case of NMR spectroscopy. You can see carbon disulfide, carbon tetrachloride, deuterium oxide, deuterioacetic acid, deuterioacetate, acetone, and you can see where these are creating problems in which ranges, and deuteriobenzene, deuteriochloroform, deuteriodimethyl sulfoxide, deuteriomethanol, deuteriopyridine, deuteriotrifluoroacetic acid, tetramethylsilane. So it was about the shielding and deshielding. How can you calculate that how many signals will be observed for a particular compound and at which position? What kind of protons will get shielding and what kind of protons get deshielding because of the surrounding electrons, because of the induced secondary magnetic field. Hope you understood this shielding and deshielding. Thank you. Hello friends, we are discussing about the NMR spectroscopy. To detect a compound for NMR spectroscopy, we need to follow, radio waves on a particular compound. And the proton of a molecule has a precession motion because of precessional frequencies or have a particular kind of precession, that is, and when this precessional frequency felt by a proton in a applied magnetic field becomes equal to the frequency of applied magnetic field, this is called a resonance condition. And when this resonance happens, there is a transition, or we can say flip of a proton, and because of this transition a molecule had a absorption from the radio frequency region. So we have discussed about how the molecule absorb radio waves, how shielding and deshielding took place, how can you detect the number of signals for a particular kind of protons. We have discussed about the relative positions because of electronegative effect, because of hydrogen bonding, because of anisotropic effect. Now the intensity of signals. The area under an NMR signal is proportional to the number of absorption protons. An NMR spectrometer automatically integrates the area under the peaks and prints out a stepped curve, or we can say integral on the spectrum. The height of each step is proportional to the area under the peak, which in turn proportional to the number of absorption protons. Modern NMR spectrometers automatically calculate and plot the value of each integral in arbitrary units. You need not to do it, it will done by the spectrophotometer. The ratio of integrals to one another gives the ratio of absorbing protons in a spectrum, and note that this gives a ratio, not the absolute number of the absorbing protons. Let us discuss, let's take an example. How can we calculate the number of protons by the integrated area of a signal? See this spectrum. Here you can see three signals are here, signal A, B and C. and moreover you can see the area also, integrated area, which is calculated by the spectrophotometer. This is 54, 23, 33 for each signal. This is the question, determine the number of proton giving rise to an NMR signal. A molecular formula, here you can see C9H10O2 gives the following integrated proton NMR. So how can we calculate the number of proton for each signal? This is the step number 1. First of all, we need to determine the number of integration units per proton by dividing the total number of integration units by the total number of protons. First of all, total number of integration units, as you have seen, we can calculate 54, 23 and 33. It will be 110 units, and total number of protons were, you can see over here, 10. So we have to divide this number of protons to the total number of integrated units, and we will get this value, that is 11 units per proton. Now step number 2 is determine the number of protons giving rise to each signal. So we can calculate for each signal the number of protons. To determine the number of proton atoms giving rise to each signal, divide each integration value by the answer of step number 1 and round to the nearest whole value. You can see the value comes out to be 110 by 10, and this will comes out 11 units per proton. So how can you calculate the number of proton for each signal? The integrated value for the particular signal divided by the number of units per proton. So it will comes out 4.9. For second signal we get 2 proton, for third signal we will get 3 protons, and we can round it off for 5 protons. So for first signal the number of proton comes out to be 5 proton, for number 2 signal or B signal 2 protons, and for signal 3 protons. Now what is spin splitting? First of all, we need to say the spectrum of this molecule, that is Br, CH2, CH, Br2. Here you can see how many signals are there? 2 signals, because this proton is different in environment with respect to these 2 protons. 2 signals are here, 1 signal is there, you can see 2 peaks and doublet. Which kind of doublet? You can see the intensity of the peaks, these are equivalent in more or less. And for this proton CH, 3 peaks or triplet will observe. Why it observed in this manner? For these 2 protons we get a doublet, for this proton we get a triplet. Why we get this kind of splitting of the signal? Because of spin splitting. And what is that? Peaks are often split into multiplets peaks due to magnetic interaction between non-equivalent protons on adjacent carbons, and this process is called spin splitting. And the splitting is into one more peak than the number of hydrogens on the adjacent carbons, and this can be n+1 rule. The relative intensities are in proportion of a binomial distribution. You can see over here, this is according to the Pascal triangle, and the sets of peaks in a multiplet. For 2 we can say doublet, for 3 triplet, for 4 quartet, for 5 pentet, for 6 hextet, for 7 heptet. And you can see the rough idea. If it is singlet, the intensity will be singlet. For doublet, the intensity will be equivalent, we can say 1:1 ratio. For triplet, it will be 1:2:1. You can see the intensity of middle one will be the double as with respect to the adjacent. For quartet, we get 1:3:3:1. For pentet, we get 1:4:6:4:1. This kind of pentet 1, 2, 3, 4, 5. For hextet and for heptet, so on. Rules for spin splitting. Equivalent proton, we need to understand first, do not split at all. You know what are the equivalent protons? First of all, we need to identify what protons are equivalent in nature or what protons are non-equivalent in nature. We have to see the surroundings, or we can see the environment at adjacent carbon atom or any other atom present with adjacent to these protons. Look at these. This is H3Cl. These three protons are chemically equivalent, so no splitting occurs. They will give only a single NMR signal. Now look at this structure. These two protons are same here, no splitting occurs because these are chemically equivalent. So we have to see them chemically whether they are equivalent or non-equivalent. Protons that are farther than 2 carbon apart do not split. You can see when we see these two protons, these are further apart, so no splitting will observe. But if they are present at adjacent carbon atom, definitely splitting will be there according to the number of protons. If we need to look the signal for this proton, we have to see the number of these proton. If there is one, so for this proton we will get only a singlet proton. And HNMR spin splitting, again if HA and HB in this case are not equivalent, splitting is observed. You can see these two are same, these two are on the adjacent carbon atom. Splitting is not generally observed between protons separated by more than 3 sigma bonds. This is the example, 2-butanol. You can see the number of sigma bonds. We can write this CH3 in this manner. We can open this bond and you can see it's 1, 2, 3, 4. There are 4 sigma bonds. So this proton and this proton are separated by 4 sigma bonds. So no splitting will occur. Same here, you can see ethyl methyl ether. Again we are writing this proton in this manner. So these HA and HB are separated by 4 sigma bonds. So again no splitting will occur. So we have to look carefully where the splitting will occur and where the splitting will not occur. The frequency difference measured in hertz between two peaks of doublet and is called coupling constant. With no adjacent hydrogen atom, the absorbing protons feels only one magnetic field and only a single signal will observe. If there is one adjacent proton, the absorbing proton feels two different fields, one felt by itself and another felt by the adjacent proton. So they absorb at two different frequencies. Simple, the doublet will observe for this kind of proton. One adjacent proton splits an NMR into a doublet due to n+1 rule. Nuclei which are close to one another could cause an influence on each other's effective magnetic field. This is called spin-spin coupling or J coupling. Each spin now seems to has two energy sublevels depending on the state of the spin, and it is coupled to, you can see, AB and BA proton, and this kind of coupling will takes place. And the magnitude of separation is called coupling constant and has units of hertz. Again you can see over here the spin-spin splitting. If we see this proton, it will split due to this proton. If we see this proton, it will split due to this proton. So we will get this kind of splitting. And here you can see this proton, two equivalent protons have this kind of environment. So coupling will take place with this proton as well as for this proton. For this particular proton, the coupling would take place for this proton, for this and this. So three equivalent protons, and you can see how the spectrum split, doublet, triplet and quartet, and you can see the coupling constant also, the distance between these two peaks. Now The another question is over here. How can we deduce the structure of an organic molecule with the help of NMR spectroscopy? Using proton NMR spectroscopy, the structure of unknown compound, let us say X, that has the molecular formula C4H8O2 and also contains an absorption in the IR spectrum. Because you are aware that when we have discussed about the IR spectroscopy, where we can easily calculate, or we can easily analyze the particular kind of functional group, whether it is a aldehydic molecule, whether it is a ketonic molecule, whether it is a carboxylic acid or carboxylic acid derivatives. So this is the data which is given in question. Here you can see there are 3 signals, and this signals, the integrated area you can see 15, and it is a triplet in nature. This is the another signal which is observed at this value. This is the values of delta from 0 to 8 in parts per million. So 11 integrated part, and you can see this signal is when we see it in a elaborated manner, this is a quartet, and this is the another signal which is observed at approximately 3.7 delta value, and the integrated area is 14. So total 3 signals are there, and you can see this is a triplet A, integrated area 15, quartet B, integrated area 11, for singlet integrated area is 14, and these are the values. So how can we proceed for this to solve this question? How can we proceed to solve a particular kind of structure of unknown compound when we are having molecular formula and another information that this carbonyl group it get absorbed in IR range? So definitely there is a functional group, carbonyl functional group, but what kind of functional group is there, what kind of carbonyl group is there, let us discuss in detail. First of all, determine the number of different kinds of protons, that the chemically different protons we need to calculate, we need to observe. The number of NMR signals equals to the number of different types of protons. We have discussed in detail that there are only 3 signals, so there are 3 types of equivalent protons are there. This molecule has 3 NMR signals A, B, C, and therefore 3 types of protons we can nominate like this: HA, HB and HC. Step number 2, use the integration data to determine the number of protons on each signal. Total number of integration units 14 plus 11 plus 15 is equal to 40 units. Then total number of protons we have seen from the molecular formula, this is 8. So when we divide this total number of integrated unit by the total number of protons in a molecule, we get the 5 units per proton. So divide each integration value by this answer, that is 5 unit per proton, and round the nearest whole number as we have done in previous case also. We get how many protons? 3 protons on signal A, 2 protons on signal B, 3 protons on signal C. So 3 equivalent protons, usually we can say it will be a methyl group CH3. 2 equivalent protons we can easily say it will be a CH2 group, and 3 equivalent protons again we can say it will be a methyl group. Let us say these are the possibilities. Step number 3, use individual splitting patterns to determine what carbon atoms are bonded to each other. So these are the possibilities. Start with the signals. Signal C is due to the CH3 group with no adjacent non-equivalent proton. Possible structures include, we can say, because oxygen is also there, so we can say these are the possibilities. Because you see there is a singlet. So we can say these are the three possibilities: CH3O, CH3CO, or we can say CH3 attached to that type of carbon atom which is having no protons. If there is a proton, then definitely splitting should be there, but when we say that it is a singlet proton, so it comes in conclusion then there is a no proton adjacent to these three protons. Because signal A is a triplet, there must be two protons CH2 group on the adjacent carbon. Because signal B is a quartet, there must be three protons, the CH3 on the adjacent carbon, because we have observed from the Pascal rule that if there is a three protons adjacent to one proton, then quartet will be observed. This information suggests that X has an ethyl group CH3 CH2. So we can say an adjacent CH3 group causes the splitting due to the two absorbing protons, so quartet will be for signal B, and due to three absorbing protons, another adjacent CH2 group causes the splitting, and concluding that there is a ethyl group. To summarize, X contains CH3, CH3 CH2, or we can say carbonyl group also from IR data. Comparing these atoms with the molecular formula shows that one atom, or we can say one oxygen atom, is missing, because oxygen atom, we are very much aware of the fact that oxygen atom do not absorb in proton NMR spectrum. Their presence can only be examined the chemical shift of proton near them. Oxygen atoms are more electronegative than carbon. We are very much aware of this fact because of the from the periodic table, thus de-shielding and shifting their absorption downfield. Now step number 4, use chemical shift data which we have observed. You can see the chemical shift data. The singlet absorbed at 3.7, the quartet absorbed at 2.3, and triplet absorbed at 1.5. So with the help of the that rule that which protons are shielding and which protons are de-shielding, we can analyze the structural pieces, what kind of possible structure for compound B. Use chemical shift data to complete the structure. In possible structure A and B are possible for X. This is the structure A, that is OCH3 group is attached to this carbonyl group, and there is a ethyl group in this kind of a structure, or we can say this kind of a structure is also possible. So which one is correct? It can simply concluded on the basis of shielded and de-shielded. If structure A is correct, singlet due to CH3 should occur downfield. If B is correct, the quartet due to CH3 should occur downfield, because we have seen from the spectrum that this singlet observed at downfield at 3.7, because the NMR of X has a singlet, not a quartet, at 3.7 downfield, therefore structure A is correct. So on the basis of shielding and de-shielding, we can conclude that which kind of structure possible for a particular group, for a particular compound. And you can see this is the 3-dimensional structure of NMR. This is the delta value, and this shows the intensity of a peak. And we are not discussing right now the coupled spectrum due to proton NMR and due to 13C NMR, but you can see what kind of spectrum observed when proton NMR and 13C NMR coupled to each other, and what kind of spectrum will observe. So you can see this kind of dots will observed for a particular molecule. So we have discussed about the NMR spectrum in details. We have discussed about the shielding effect. We have discussed about the de-shielding effects. We have discussed about the effects which can affect the de-shielding and de-shielding. And we have discussed about how can you calculate the number of signals by the integrated area for a particular signal. We have discussed the spin-spin splitting or according to Pascal triangle, and we have also discussed how can you calculate or how can you analyze the spectrum of a particular compound having molecular when the informations are giving according to the molecular formula, but you need some assistance also from the other kind of spectroscopy, from other informations also, like in this we have discussed the question we have discussed in which we are given by the IR value also from carbonyl groups. So, we cannot analyze the spectrum of an organic molecule simply by proton NMR spectrum. We need some other help also from ultraviolet visible spectroscopy, from IR spectroscopy also. So, hope you understood this lecture. NMR spectroscopy, you can calculate the proton NMR, proton skeleton, or we can say the equivalent, chemically equivalent protons or chemically non-equivalent proton of a particular molecule, and you can elucidate the structure of a molecule with the help of other spectroscopy also, ultraviolet visible spectroscopy, IR spectroscopy, as well as mass spectroscopy. In coming lectures, we will discussing about the mass spectroscopy in details. Thank you so much.
With this note, thank you, ma'am. Thank you so very much for giving us a vivacious session on NMR spectroscopy. Ma'am, as we talk about the subject called science, it is all application based.
Yes.
And if we talk about spectroscopy, so what are the applications of spectroscopy?
Yes. Spectroscopy is the advanced technique. You can elucidate any structure, organic molecule with the help of different types of spectroscopy. Like we can take the help of ultraviolet visible spectroscopy. You can calculate the conjugation, the homoannular, the heteroannular structure in a given organic molecule. With the help of IR spectroscopy, you can calculate, you can analyze the particular kind of functional group in an organic molecule, which when we are doing manually or from the classical practicals, you have to take care of many, you have to take care of help of many reagents, but instrumentally you can easily calculate. It is more precise and concise. From NMR spectroscopy, it is very important tool to analyze any organic molecule. Let's say if you want to identify the cancerous cell in our skull, you can easily calculate or you can easily analyze the cancerous cells also from the NMR spectroscopy, or you can say from proton NMR spectroscopy, from carbon NMR spectroscopy. So, it is advanced technique. It helps a lot in medicinal field also, not only for researchers in chemistry, but also in other areas for botanists also. If you want to analyze any organic molecule present in a extract of medicinally extracted plant, you can easily analyze the what kind of structure is there in extracted compound from the medicinal plants. So, it is not only helps for chemists, but it also helps for many researchers, not only medically, but for botanists also.
So, thus we can say that the particular area spectroscopy is for the betterment of the society and for the betterment of the humanity. Dear friends, with this note, we would like to thank Dr. Vandana once again for her precious inputs to the lecture, and we believe that you have learnt a lot on spectroscopy, specifically NMR spectroscopy today. If you have any queries, any questions, then do write to us at info.cec@nic.in. Your feedbacks and suggestions are also welcome. If you want to have a session on a particular topic which you feel so is not covered till now, then also you can write to us. We'll try to conduct the session on the particular topic in near future. Dear friends, this is the last session of this month. Now we would be meeting in October, and if you want to know what lectures we are going to conduct in the month of October, for that you can definitely have a glimpse on our schedule, which is uploaded or is going to be uploaded on CEC website. Our website is www.cec.nic.in. There you can find EduSat schedule, and with the help of schedule, definitely you can see all the 4 transmissions daily from Monday to Friday. So we are taking your leave now. We'll be meeting on Tuesday. Till then, take care. Goodbye. Thank you, ma'am. Thank you so very much.
Thank you.